Now for the exact system rule, we have this rule called the CIP rule, CIP not Community Involvement Program, Karn Ingo Perlock sequence rules. It is used to guide us how do we rank the order in terms of priorities attached to a particular carbon atom. So if the lower and lower are on opposite side, then it's E. It means the higher and higher are the opposite side as well. So this is E. If the higher ones are on the same side, it's called Z. If the higher priority groups are on the opposite side, we call it E. If they are on the same side, they are called Z. So this is similar to the same size cis, but we cannot call these cis because they may not be the same, okay, or these two may not be the same. But you can remember by using this hack over here, like this Z is like cis, it's like but it's different. Then of course E must be the so-called trans-like one, okay, but again let me clarify, they are different. This something like cis, then trans-like. So how do we rank them in terms of a higher or lower priority? We look at the atomic number of the direct atom they are attached to. So for this case, this carbon here, we cut into half first, okay? We look at one side of the double bond. We are comparing chlorine against carbon, not the whole thing up because it's just a single atom that's attached to it. CCl. Cl has a higher atomic number 17, it will trump 6, so higher. 1, this is 2, lower priority. H, this is the lowest rank. 1, this is 2, this is 1, so you see higher rank on opposite side is an E isomer, so we put bracket in italics, E, close parenthesis, hyphen 2 hyphen chloro, but2ene. For that case, it's the opposite, low rank on the same side, Z isomer. Now for rule number 2, if a decision cannot be made by ranking the first atom in the substituent, look further on, the second, third, fourth atoms away from the double bond until the first difference is found. It is like if you play cards. Just don't gamble. If you play poker, you play your best hand first, right? So let's say you have a set of cards in your hand. You try to play your best card first. So let's do this. Now we have a junction here. We are comparing methyl against ethyl. Which one has a high priority? So you see this carbon here has got 3 cards called H, H, and H. The second guy, second set here, he got H, C, and H. So the best card for him is a carbon because it's the highest priority. So you throw it out and fight. C. The first guy, the best is still H. So H against C, C will win, and that's why this is higher. For the second case at the bottom, this guy has C, C, H, C, C, H. That guy has a C, H, H. So what you do is, you put the best card up front, then you fight. C goes with C, no fight. Draw. Next one, H against C against H. So we have a winner, higher priority. For here, we have OH. O are the same, right? So you see the best card. There's only one card, H. This got carbon, so win. C, it's got an N. It's got a Cl, the best one, winner. Rule number 3. If you have multiple bonds, it is equivalent to you are bonded to the atom again. So this represents HOO. And then further on, the O bonds back to the carbon twice. So this oxygen is bonded to CC. Okay, so that's how you translate to this picture. Let's try some example. Apparently this has a higher priority because H is always the lowest. What about this side? Take a look here. C, draw. H, C, C, H, H, O. Alright, so who is higher? O. O beats carbon. Ta-da! So since the higher ones are on the same side, it will be Z isomer. I'm going to let you guys know that, right? This structure is imaginary, okay? Please don't quote this. Because you see, oxygen is supposed to have 2 bonds coming out of itself. Because it's in group 6, Triocogens. Because it is in group 6, the Chalcogen series. But here, this is just used as example to determine whether it is of a higher or lower priority. This bond here is real. This is imaginary. Take note. Right. Here you see molecule with a double bond here. This is a cis isomer because your H at these 2 junctions, they are identical. They are on the same side. So here we have a Z trichosline, a housefly pheromone. This is used to get rid of flies, okay? It comes from a female version. Because sometimes, right, you know, the opposite gender is a bit turned off, so you don't want to mate with them. And you give off this kind of pheromones to repel them. Pheromones doesn't mean you must attract your partner, but it can also be used as a kind of repellent towards them. On the right side, you have more pheromones. Very common with double bond here. And they're mostly Z isomer. Bottom, algal pheromones from algae. Okay, the right hand side, C star pheromones. This is a bit rare because they're all E. Now for the stability of cis and trans isomers, we can do some little comparison. We should know that, right, by the drawing, the cis has a big groups that's closer together, so we have a bit of steric strain, which is not desirable. But the trans, you are avoiding it because the big groups are on opposite end. So this is very much of a lower energy than the one before. And how do we prove this? We let both molecules undergo the same reactions called hydrogenation to make a saturated molecule called a butane. Butane is a colorless gas that's used mainly as a fuel, and we found that the enthalpy change for the hydrogenation of the trans isomer is less exothermic. So what does this show? Now imagine that, right? This is the energy profile. Oops. This is energy. We note that cis has a higher energy because it's not so stable, and trans is of a lower energy because it's more stable, and the reaction is exothermic, so it goes down. Right here, this is your butane. Okay, that is the trans version. This is cis. So you see from here, it is more exo than trans, and indeed we are proven correct. But take note of this, Spectra substituted alkene is more stable than trisub. In turn, it's more stable than disub than mono substituted alkenes. Okay, so on the left hand side here, this is the most stable, and that is the least stable. Alright, and we could tell by, again, experiments. So these are the data. So how do you explain that effect? Something called hyperconjugation. Hyperconjugation. It shows the stabilizing interactions between the carbon-carbon pi bond and the adjacent CH sigma bonds on the substituents. The more substituents there are, the greater the stabilization of alkenes. Alkene, that's alkynes. They have pi bond, both of them. Pi bonds are regions of electron rich density, and they like to seek nucleus because they are so electron rich, they are so negative. So they are called nucleophiles. Nucleo means the nucleus. Nucleus has a lot of protons, positive charge, so they are nucleophilic. That means they are also Lewis bases. So they react with electrophiles, which are the Lewis acid. Let me give you a simplified version of an electrophilic addition. We have a nucleophile that's full of electrons, which is an alkene, attacking an electrophile, H plus ion, without any single electron. So the pi orbital electrons here will just attack the H plus and form a bond. You get this. And this is a carbocation, because you see a carbon carrying a positive charge. That's what we call it, a carbocation. Is it stable? Is it stable? Alright. For structure of carbocations, Note that the carbocations are planar about the carbon center carrying the plus charge. It has got 3 groups attached to it, and this is equivalent to a trivalent sp2 hybridized carbon with a vacant p orbital, which is on the axial position, the other bonds on the plane. Alright, so this is perpendicular to the plane of the carbon. Now recall in hyperconjugation in alkenes, I have not finished telling you just now. What happens is, right, the more substituents there are, the greater stabilization of the alkene. So in hyperconjugation, this is rather similar, because now if we have the CH bonds here, this is a sigma orbital that will interact with the empty p orbital of the carbocations carbon. You see, there's some kind of interaction, right? When it is aligned, then they will interact. And when we have more of these interacting, it is more stable. So that explains why the alkene stability is in such order. And the same goes for carbocations. Inductive effect. It says that the more alkyl groups that are attached to the positively charged carbon, the more electron density shifts towards the charge and more inductive stabilization of the cation. So basically you can take it as the R group, they like to release electrons, so they like to push electrons to a side. And if the carbon in the middle right now is trivalent, that means only having 6 electrons, that's a shortfall of 2, because all these elements here like to have an octet electronic configuration. So what happens is when you have more R groups, these groups here push electron density closer to the carbon. Take note, it's just pushing, not giving. Pushing closer to the carbon so that now the carbon feels more electron density. It feels more electron rich, so it doesn't feel so poor, so deprived of the electrons, and that's why it's more stable. On the other end of the spectrum, methyl group, they are all H's. H's doesn't donate electron, they don't even have enough themselves. So they can't push electrons, and that's why the C plus in the middle feels very deficient, feels very hungry, and that's the reason why it's not stable. It doesn't like to exist for a long period of time. In the reaction mechanism, you see right here in this alkene, we put the H plus there. There's only one way of forming it. This is a secondary carbocation. Recognize it because the carbon plus charge has got one H beside it. Now, regiochemistry. This is some form of selectivity we have to understand in chemical reactions, organic chemistry reactions. Regio stands for region, the location. Now, for this asymmetric alkene here, if we put the H plus, we have got 2 possibilities. One, H goes here. The other one, H goes there. What happens now? We draw both, okay? And see. For the first case, we have a tertiary carbocation. For the second case, we have a secondary carbocation. And because we know that tertiary carbocation is the most stable among all, we take this. This is not formed. We take the one that's the most stable. Now for the mechanism, step 1 is the pi bond here breaks and pick up the H from the electrophile. Then the bond will break from the O and H in the hydronium ion. Because we know the H, there's only a single 1s orbital, it cannot form more than one bond. So when you form one with it, you got to break the other one. So it forms this still an electrophile because now it contains a positive charge, a carbocation that will attract a nucleophile, which is full of electrons. You see now the water has lone pair, which will attack. You see this arrow here? The arrow shows the movement of electrons, where electron is flowing to. The last step, using another water molecule, it will pick up the H, right? Goes back to the O, loses the plus charge on the O, and you get the alcohol. 2-methyl-propan-2-ol.